Space elevators are fascinating concepts that have been explored for decades as a possible solution to overcome the challenges of space exploration. Imagine a revolutionary method that would allow us to escape the dependence on conventional rockets, making space travel more efficient and accessible. In this video, we will explore the fundamentals, challenges, and promises of space elevators, diving into the exciting field of space engineering. Space elevators, also known as space lifts or geosynchronous elevators, are theoretical structures aiming to provide a means of transportation to space, eliminating the need for traditional rockets. The essential structure of a space elevator consists of a cable extending from the Earth's surface to a station or counterweight in geostationary orbit. This cable would be anchored to the Earth and extended vertically, with one end attached to a space platform and the other anchored to the ground, creating a fixed connection between the 2 points. The core of space elevators lies in the idea of creating a physical connection between Earth and space, replacing, or at least complementing, traditional launch rockets. Instead of relying on powerful explosions, the proposal is to establish a road that allows efficient transport of cargo and even humans to higher orbits. One of the main challenges associated with space elevators is the choice of materials to build the cable. The material must be strong enough to support its own mass, resist natural forces such as winds and storms, and be light enough not to collapse under its gravity. Carbon nanotubes and graphene are often discussed as promising materials due to their unique properties. The cable of a space elevator would be under extreme tension along its length. Managing and distributing these tensions effectively is a significant challenge. Engineers need to create a structure that can withstand not only the static load of the cable itself, but also the dynamic load generated by the upward and downward movement over time. Positioning the upper end of the cable in geostationary orbit is crucial for the stability of the space elevator. Achieving precise alignment and maintaining the orbit synchronized with the Earth's rotation are significant technical challenges. The precision required to ensure that the upper end remains fixed relative to the Earth's surface is an obstacle that requires advanced control and monitoring solutions. Moving loads along a cable hundreds of kilometers long will require efficient propulsion systems. The energy needed to propel the loads up and down needs to be managed effectively. Research in propulsion technologies and energy systems is essential to overcome this challenge and make space elevators a viable reality. In addition to technical challenges, engineers face the task of gaining public acceptance for such a bold idea. Moreover, the economic viability of space elevators is a critical consideration. Convincing governments and investors of the long-term benefits and financial sustainability of this venture is an additional challenge. The geostationary orbit, located approximately 36,000 kilometers above Earth, is crucial for the success of space elevators. At this altitude, the orbital speed of the cable would match the Earth's rotation speed, allowing the structure to remain stationary relative to the ground. This is essential to facilitate continuous access to space. In addition to technical challenges, space elevators face environmental obstacles, such as exposure to intense solar radiation and space debris. Various solutions have been proposed, from active protection systems to strategies to avoid collisions with debris, demonstrating the complexity of the engineering required to make this vision a reality. If space elevators can be successfully built, they promise a range of advantages. A significant reduction in the costs of launching payloads into orbit is one of the most highlighted benefits. Additionally, the possibility of performing repairs and maintenance on satellites without the need for highly complex manned missions could revolutionize the space industry. The ability to transport heavy payloads more efficiently could propel ambitious projects, such as the construction of large space structures like the Dyson Sphere. You can check out my video on the Dyson Sphere here on the channel by clicking on the cards. While the idea of a space elevator is intriguing, it is essential to explore potential adverse scenarios that could occur. A hypothetical simulation of the fall of a space elevator allows us to examine the scientific and technological implications associated with such an extraordinary event. Imagine you are at home, enjoying the spectacle of the sunset through the window, with your thoughts floating between the nuances of the evening. Suddenly, a deafening roar breaks the silence, shaking the foundations of your house. You rush to the window, incredulous, only to witness a bewildering sight. The road connecting Earth to space, the much discussed space elevator, shatters before your eyes. The view is surreal. Twisted cable pieces and fragments of the orbital platform spiral down towards the ground. That link that should connect humanity to the cosmos is now broken, casting shadows over the dreams of space exploration. The sound of the rupture echoes like a celestial lament, a symphony of distorted metal that contrasts with the serenity of the sunset. The road to the stars, now fragmented, represents not only a physical rupture, but also a symbolic collapse of aspirations to reach the unexplored. The fall of debris is a chaotic dance of physics and gravity. Each piece of the space elevator follows its trajectory, a frenetic and unpredictable choreography. Some fragments move slowly, while others dive into fast spirals. The atmosphere, which should be the protective boundary of Earth, is now a stage for a rampant cosmic performance. The stillness following the initial roar is interrupted by pinpoint impacts. Space debris collides with Earth, raising dust and debris. Distant areas are affected, while imagination runs wild with fear of the unknown. What will happen at the impact points? How will nature react to this unexpected shock? As the news spreads, scientists and engineers begin to analyze the situation. A team of experts is convened to investigate the causes of the collapse. Among them, aerospace engineers, physicists, and ecologists unite to understand the details of what seemed impossible. Beyond material damage, the fall of the space elevator reveals unexpected environmental impacts. Space debris releases unknown substances into the atmosphere, triggering concerns about long-term effects on air quality and climatic conditions. While highly improbable due to rigorous safety measures and designed redundancies, this event offers us an opportunity to explore the scientific complexities involved. The fall of a space elevator would involve a complex interaction of forces, including Earth's gravity, the cable's inertia, and atmospheric resistance. The behavior of the cable during the fall would be crucial, as different sections may experience varied forces, leading to deformations and extreme tensions. Considering the significant height a space elevator could reach, potential ground damages would be a concern. Simulated models would indicate the likely impact areas, highlighting the need for exclusion zones to minimize risks to inhabited areas. Such a simulation would also emphasize the importance of emergency response systems and evacuation plans. How would authorities and space organizations respond to such an extraordinary situation? The effectiveness of safety protocols and the ability to evacuate potentially affected areas would be crucial in this context. Beyond immediate impacts, the simulation would allow examining the long-term repercussions for space research. New challenges and safety considerations could arise that would shape the future development of space elevators and associated technologies. Despite their promise, space elevators still face significant obstacles, from technological challenges to issues of funding and public acceptance. Exploring ways to overcome these obstacles is crucial to transform this vision into a tangible reality. International collaboration and ongoing investment in research and development are fundamental elements for advancing this innovative field. The in-depth conclusion leads us to a journey of reflection. The pursuit of space elevators is not just a technical matter, but an exploration of our own limits, a test of resilience and innovation. Answers and solutions emerge not only from spreadsheets, but from introspection and understanding of our roles as explorers of the cosmos. Space elevators represent an exciting vision for the future of space exploration. While they remain in the theoretical realm for now, continuous progress in nanotechnology, materials engineering, and space exploration may eventually make this vision a tangible reality. The journey toward space elevators offers a glimpse of the transformative potential that space engineering can bring to humanity. By exploring the basic concept of space elevators, We are witnessing the first steps toward a new era in space exploration, where the boundaries of space become more accessible than ever. We stand at an exciting frontier where the stars are no longer unreachable, but accessible through a road connecting Earth to the cosmos. This video demanded a lot of work, and I am just starting on YouTube. Your support makes all the difference, and I would be honored with your subscription. If you enjoyed the content and want more, I ask that you subscribe and activate notifications. It would be a great help to me. I'll see you in the next video. Until then, take care.